Hello, my name is Mohamad Barada. Today I'm with you on regarding my study that I would like to present. My topic is an in-house overset supersonic solver with great refinement capability on parallel environment. A little bit about me at the beginning. My name is Mohamad Barada. Thank you for joining this presentation. I am actually a PhD student from Istanbul Technical University. I graduated from there also my master's degree and bachelor's degree in aerospace engineering. I also worked in Turkish aerospace industry as a research contract for the university. Some of the topics that I worked on are supersonic inlet numerical analysis and transonic airfoil bump methodology. Also, I'm a co-manager for a company called Config Digital Solutions. We develop software programs. Some of our softwares are Cinder, which is a digital asset trading framework. And at the same time, we also develop Config UPS, which is a configuration software for UPS systems. As you can see, my research interest is mainly concerned with CFD process speedup and automation. So in our topic, I will subclassify my presentation to sub-categories. At the beginning, we're going to talk about the study, what motivated us to work on it, the library which we used, about how it works and in the literature. And then finally, we'll talk about the aims and the scope of the study. Then we're going to talk about how we implemented it to our in-house solver. And then we're going to talk a little bit about our solver. Then moving forward, we're going to talk about the performance of the integrated solver in terms of accuracy and at the same time parallel performance. Then finally, we're going to wrap it up with some conclusions. Moving forward, the motivation for our study is rather simple. We're really interested in hypersonic flow analysis, and when we talk about hypersonic flow, we're mainly interested about heat transfer prediction. In heat transfer prediction, there are some key players. Those are primarily the radiation modeling, the shockwave boundary layer interaction, conjugate heat transfer, and also we would like to expand it to complex structures. As a result, you can already imagine that the computational cost is going to be rather high. So as a result, we would like to search for some strategies to reduce this cost. Some of those strategies is the overset grid implementation or also using adaptive mesh refinement. So indeed, those are the strategies that we try to follow, and we try to develop our in-house solver. This solver we actually presented in a conference in Ankara, the International Aerospace Conference. Unfortunately, however, this code had some limitations. It was limited to serial computation, and it was limited to the 2D cases. Additionally, and most important, it was limited to single tree as a basis for our AMR, which is very memory restrictive. So as a result, we recently were considering expanding the horizon just to solve those problems. We discussed at length and we found out that using an integratable open source library that provides parallel scalable multi-tree structure is going to be the most suitable for us. Indeed, we actually found one which is P4ACE. It's an open source library written in C developed by Barada in 2011. It's very scalable. And it has been used in multiple flow problems. For example, Brazil in 2011, he actually worked on the Tyler vortex degree and the NACA 0015 wing. He actually achieved very nice results on parallel environment. Also, Pan et al. In 2011, he worked on finite volume-based solver with P4ACE integration for incompressible viscous flow, and it provided very nice results. So how does P4ACE actually work? It's based on the Z-Morton curve. As a space filling curve that fills the space, and it's cut into multiple partitions for parallel solution. The manipulation of the P4ACE, which is essentially a forest of octarees, is actually done by using some functions which have some callback functions provided by the user. So some of those are P4ACE iterate, refine, coarsen, partition, and balance. Partitioning is done also in real time. P4ACE hasn't really been used in literature to our knowledge within the context of overset AMR for finite volume based supersonic flow solver. However, this general idea of overset and AMR has been done in literature. For example, in Kenway et al., he actually worked on the implicit strategy for overset grid assembly, which is also parallel. For example, Perron et al., he actually used single octree overset AMR with interpolation for different levels. but he didn't talk about the parallelism approach. Polyamid also, he worked on an AMR strategy for conformal grids, however, he didn't talk about the overset strategy. So in this study, and what I plan to actually discuss from our results, is actually we're going to assess the integration of P4 within overset AMR-based supersonic hypersonic solver in terms of solver accuracy and the parallel performance. Also, as a side note, since we're dealing with overset grids, we're going to talk about conformal grid. The conformal grid is going to be inputted from open form tools, which is primarily block mesh. So the implementation of P4S into our code is rather simple. There are three junctions at where we implemented the overset grid assembly, the AMR process, and finally the partitioning and parallel communication. In overset assembly, we essentially use P4S as the foundation for our Cartesian grid. So from there we generate a forest, which is like a collection of octant nodes for multiple trees. Then from there we refine it based on the proximity. Then we finally, for each octant, we generate an associated grid. For example, in this case, as you can see in the figure, it's a 2x2x2. Then from there we do the assembly process. By using the conformal grid wall cells, we tag the octants that are intersecting with them. Then from there we essentially create a hollow. Then from there we choose a flooding seed from the inside, then we fill it to generate the hole. Then this is done in parallel, where each core that has its octants runs like a specified number of sweeps to generate the flood and fill the hole. Finally, after we do that, the outermost layer of the hole is used as receiver octants. As for AMR, we also use P4East. Simply what we do is that we call the P4East manipulation functions, for example, refine, coarsen, and balance, and to each of those we actually provide it with a callback function. And those callback functions are essentially an assessment if the octant require refinement or coarsening. Some of our techniques for AMR, we use bisection method for the threshold acquisition. This has been used by Perron in 2013. And also we use undivided difference for the sensor function. This has successfully been used by Polyam. And as a value for the threshold, we use pressure, which has seen very successful results for capturing regions of interest, for example, shock waves, as you can see on the right by Hanke et al. In 2020. So moving forward, there is, however, one problem with P4East. That's mainly with the coarsening. If you do coarsening, sometimes it actually does not obey the balance rule, where you have one restricted refinement level difference between adjacent octants. So in order to remedy this problem, what we do is that we do coarsen, then we do rebalance. However, to ensure that we do not lose the data that we lost from coarsening, then re-refining from the balancing, we actually temporarily cache it, then we re-provide it. However, if the octant is permanently coarsened, then we delete that data. Moving forward, in terms of partitioning, also P4East helps us. Of course, with the conformal grid, we partition it using OpenFOAM tool, since we also use it to generate the mesh. However, for the Cartesian grid, using P4East partition, we partition it to the cores that we're using. Of course, we also apply a rule that children octants of the same parent are on the same code. That allows us to do coarsening operation without having to communicate between cores. In terms of communication, there are three communication classes. The first one is conformal to conformal within the conformal grid. This is done using this classical approach via MPI, where we communicate the ghost cells between each other. As for the Cartesian to Cartesian, we communicate them by using P4East MPI implementation. Finally, for the communication between the conformal and the Cartesian grid, where it is necessary for interpolation, we actually use a broadcast approach. In the broadcast approach, the donor cells and the receiver cells of the conformal grid are communicated from the ecosystem of the conformal grid to the Cartesian grid, in other words, the P4East. Then from there, the interpolation process is done. Then the information are sent back again by broadcast for synchronization. So this is how we implemented P4East. Now for our solver, essentially the solver, just to talk a little bit about it, it solves the Favre average Navier-Stokes equation, so it allows us to apply a turbulence model. The turbulence model that we are using is K omega SST, as it has been proven to be able to solve for adversely gradient type of problems. From there, we actually use numerical schemes in our solver. Those are for-term integration, Euler explicit spatial discretization, finite volume method. As for the overset interpolation, we're using first order explicit interpolation, convective flux, Sm plus m, viscous fluxes. We're also using central scheme, second order. Now moving forward to the assessment of our integrated solver with P4East. First, let's talk about the accuracy. To assess it, we actually attack a benchmark problem that's going to be the supersonic flow over hemisphere. In this case, it's a Mach 2. The Reynolds number is 1.3 million. We're using a cluster with 12 cores, Intel Xeon Gold 6130. The data is already available, experimental data, and it has been used many times in the literature as a validation problem. For example, in Saho and Tikuri, you can see on the right, for example, in Tikuri's case where he validated his data. Our computation setup is rather simple. We're using an overset grid, one with conformal covering the hemisphere, and also a background grid. The boundary conditions are inlet outlet supersonic, and we're using no slip for the wall. The node grid resolution is 2 by 2 by 2. The max refinement level is 4. The base octant forest is 7 by 7 by 7. And we have a starting total cell count of 300,050 with a Y plus of 3 to resolve the viscous sublayer. From the test, after running the case, we also ran it with a single grid for benchmarking. We got our overset grid solution and the single grid very similar to each other, and comparative with the experimental, where you have the stagnation point, coefficient of pressure is within 4.5% error. Moving forward, you can see that the Mach contours that we were able to achieve with the shockwave well resolved with the AMR adapted to it. Now moving forward with the parallel performance, first of all, let's talk about the strong scaling test. We do the test on our single node cluster up to 32 cores with the same type of CPU. We compare it with OpenFOAM solver Sonic Foam. As you can see from our results, we have very similar performance trend to Sonic Foam. However, it's a little bit less in terms of speed up factor and parallel efficiency compared to it. This is very likely because we're running an added interpolation stage, which is non-existent in single grid that Sonic Foam is actually solving. In terms of load balancing, you can see that each core, as the grid evolves with the changing, with the evolution of the shockwave, you can see that each core maintains a similar amount of cell count to each other. There is a minor deviation between each core, and this is normal because of the bias that I talked earlier about, the rule where children of the same parent are on the same core. Finally, so to wrap it up, what were we able to achieve? We were able to achieve promising results in terms of accuracy for our solver, and we were able to provide a strong scale, prove some good scalability compared to OpenFOAM for our solver in terms of strong scaling. Of course, there was lower performance. However, there are some limitations that we would like to address in future studies. Those are primarily have to do with the conformal grid generation. Right now, we're using OpenFOAM, a block mesh tool, which is somewhat restrictive to simpler models. As you've seen, our benchmark is somewhat simple, but we would like to attack much more complex issues. Also, our interpolation scheme is kind of low order, so it doesn't really maintain the solver order. In order to do that, we would like to explore higher order flexible methods for interpolation, for example, inverse gradient or explicit Lagrangian. Finally, we would like to consider a more combined dynamic partitioning strategy in such a way that because right now our communication is being done by broadcast. However, we would like to use methods that exploit the spatial location of conformal and background grids in such a way that it reduces the communication overhead between cores. This is pretty much all about my study. I thank you very much for joining my presentation. Unfortunately, this is a recording. As much as I would like to do it live, however, due to unforeseen circumstances, I couldn't. So if you have any questions, I'm more than happy to answer them. Please email them to me at my email, barada@itu.itu.tr. Thank you very much.